Okay, welcome back. This is Mrs. Thompson. I'm getting ready to teach a section on 4.1, pages 230 to 236. Our objective today is to identify linear functions and linear equations. And we're also going to graph linear functions and give their domain and range. So let me give you a definition first of all. A linear function is a function whose graph forms a straight line. So we know how to find out if something's a function. We learned that in the last chapter. But to determine whether it's a straight line, there's a couple of strategies. Example 1 is one of these strategies. We're going to identify a linear function by its graph. So let's look at letter A. This is our goal. We're first going to determine whether it's a function or not at all. So if it is a function, then we're going to determine whether it's linear. So let me talk you through this. Let's look at letter A, and I highlighted letter A, so hopefully it shows up in the video for you. It may be a little harder in your note packet, but A shows a line leaning to the left, and what we do when we're given a graph, I know I gave you some strategies in our last couple of chapters on how to determine whether something is a function or not. What I would do is I would apply the vertical line test. So let me get my pen going here. And anytime you're given a graph, this is my advice. Let's see if it passes the vertical line test. Okay, so for letter A, if you draw a vertical line anywhere along that particular line, you will see it passes through exactly and only one point. So yes, this would be a function, definitely a function. Now, but is it linear? So that's our second thing we need to consider. So look at your graph. Is it a straight line? Absolutely, yes it is. So not only is letter A a function, it's a linear function because it happens to be a straight line. Now let's look at letter B. Again, does it pass the vertical line test? Do parabolas tend to pass the vertical line test? Well, yeah, the ones that look like that, they do. So yes, it's a function, but is it linear? So you're asking yourself, hey, is that a straight line? And you'd go, no, it's not a straight line. So it's not a linear function, although it is a function in general. It's just not linear. And then let's look at letter C. I tried to highlight it for you. Hopefully it shows up really well in the video. That line is definitely a vertical line. But is it a function? Does it pass the vertical line test? And the answer is no, it doesn't. If I put a vertical line on top of the vertical line that's already there, it would actually hit every single point. Remember what we said about the vertical line test. It can only cross at exactly one point, not all the points. So a vertical line is never going to be a function anyway. So since it's not a function, it just can't be a linear function. The only way it can be a linear function is if it's a function to begin with. And this particular line, the vertical line, letter C, it's not even a function. So hopefully that makes sense. If it doesn't, rewind me, look at the video again, and let's take a look at it. All right, flip your page. Now sometimes you're going to be given a graph like in example 1, and sometimes you're going to be given a chart like example 2. So I'm going to do several of these because this tends to be a little bit tricky, and I hope I'm very, very clear with you. So what we're going to do is we're going to determine whether these two relations are functions, and then we're going to determine whether these functions, if it is a function, is it a linear function? So let's start with the function. Is it a function anyway, at all? And so look at your x's. This is where you're focusing right here. You're looking at the x column, okay? Now, all the numbers are -2, -1, 0, 1, and 2. Hey, they're all different. That means it's a function. Remember what we said. This is something we learned in the very last chapter. You have a function if your domain are all different. If all those elements in your domain are different, you have a function. Okay, now let me show you how to determine whether it's linear. What you have to do, and I gave you a hint, so hopefully you see it right here. I'm going to box it in for you so you see it really, really good. You have to have a constant change in the x and, underline that for me in your notes, and a constant change in y. If you have both of those going on, guess what? You have a linear function. All right, so let's go back to our example here. Let me show you what it means if it's constant, okay? So we've got, start on the x side, -2 to -1. Well, what we did was we increased by 1. And then -1 to 0. Again, we increased by 1. 0 to 1, same thing, increased by 1. And 1 to 2, we increased by 1. Do you see all those numbers on the left side where they all say +1, +1, +1, +1? That is your change in your x's from one x to the next x. They're all changing by the same value. That means it's a constant change when all the values are the same like that. So looks good for the x's. Now let's check out our y's. Now how did I get from 7 to 4? You're right, I went down 3, 4 to 1, went down 3, 1 to -2, you're right, I went down 3, and then -2 down to -5, I went down 3 more. So again, we went down the same amount. We were decreasing by 3 each time. So I have a constant change in my x's right here. I have a constant change in my y's. And guess what? That means, yeah, that's linear. This is a linear function, in addition to being just a regular old function. So let's get to the bottom one. Let's see what it looks like when things don't match up, okay? So you're trying to see if it's a function, and all the x's are different. So yeah, this is definitely a function, okay? We talked about this in the last chapter. All the x's are different, you have a function. So the domain members are all different. None of them repeat. Now, is it a linear function? Remember what we're looking for. Constant change in x and, underline that word, constant change in y. They both have to happen. It can't just be one. It can't just be the other. They both happen. All right, so let's see what happens. We got -2 to -1. That means we're increasing by 1. -1 to 0, I'm increasing by 1. 0 to 1, I'm increasing by 1. And 1 to 2. Hey, it's looking good so far. I'm halfway there. I do have a constant change in my x's. That's looking great. Let's do our y's. 6 to 3, I went down 3. 3 to 2, I went down 1. 2 to 3, I went up 1. And 3 to 6, I went up 3. There's your problem right there. That's not a constant change. And so because it's not a constant change, this is not linear. It's not a linear function at all. Remember what I said. If it's a linear function, you're going to have a constant change in x and a constant change in y. All right, let's flip the page and let's put it into practice now that I've introduced the concept to you. And I'm sorry it's a little slanted. I made some copies and just doesn't look good. So just ignore it. The first thing I would do is I would take my list of ordered pairs and I would create an XY table. So I'm going to do 2, 4, 5, 3, 8, 2, and 11, 1. I really think putting them vertically in a table is the better thing to do. I think that would be very useful to you. It's clearly a function. All the x's are different. Let's see if it's linear. All right, let's start with our x's. 2 goes to 5, we're increasing by 3, increasing by 3, increasing by 3. Okay, so I have a constant change in my x. I'm going up by 3. That's a constant change. They're increasing by the same amount. That's a good thing. All right, let's check our y's. All right, 4 to 3, I'm going down 1. 3 to 2, going down 1. And 2 to 1, I'm going down 1. I also have a constant change in my y's. That means this is a linear function. And I'm going to use my shorthand so you can see what's going on there, okay? I don't want to write out function every time. That's my shorthand in case you forgot. All right, let's look at letter B. Again, we're going to do the XY table. Let's lay it out. And here we go. -10, 10, -5, 4, 0, 2, and 5, 0. All the x's are different, so I definitely have a function. Let's see if I've got a linear function, however. So I'm going from negative 10 to 5, I'm increasing by 5, negative 5 to 0, increasing by 5 again, and 0 to 5, increasing by 5. So, hey, looking good so far. I have a constant change in my x. Let's look at the y's. 10 to 4, I'm going down by 6. 4 to 2, down by 2. 2 to 0, down by 2. Oops, that's a problem. It's not constant in its change. So that means this is not a linear function. Remember, just to clear it up for you, you have to have a constant change in your x's and a constant change in your y's. If you don't have both of them, you don't have a linear function, okay? All right, let's flip to our next page. This is really super important. This is one of those state test things you just need to know. Standard form of a linear equation. I want you to memorize this formula. AX plus BY equals C. Memorize it. You never know when I might put some points on your bonus log because you remember something like that. AX plus BY equals C. That's standard form of a line of a linear equation. Now I've got some things I want to talk to you about, and right here in this particular grouping, some things I need you to notice. Okay, number 1 says if it's a linear equation, x and y are both going to have exponents of 1. We don't write those exponents. They are understood to be 1. Okay? If you have any other exponent other than 1, guess what, guys? It's not linear. Number 2, x and y are never multiplied together. So in standard form, you don't see x times y ever. It's ax plus by or ax minus by. You're not ever going to see them multiply together. So if you ever see x times y, guess what? Not linear. And thirdly, x and y do not appear in denominators, exponents, or radical signs. So if you see an x or a y in the denominator of a fraction, that's your red flag. Guess what? Not linear. If you see an x or a y as an exponent in an equation, guess what? Not linear. And of course, if you see the radical sign, not linear. Okay? Now this chart that's right here just gives you, I'm going to let you read it for yourself. It just tells you on the left, these are examples of linear equations. And on the right, these are examples of not linear equations. And I'm going to let you look at the chart. If you have a question about any of those, bring that to class and let me talk you through it. I'm happy to do that for you. All right, flip to the next page, and now we're going to apply what we just learned to this next example. We're going to graph linear functions, but we got to determine whether it's linear or not first. And if it is linear, we are going to graph it. If it's not linear, don't worry about it. Okay? So this first equation, we want to get it into this standard form, ax plus by equals c. Right now it's not. Right now this is what it says, y equals x plus 3. Notice in the equation, ax plus by are on the same side of the equal sign. And in our equation, they're on opposite sides of the equal sign. Y equals x plus 3. So we need to get the x over on the same side as the y. So we're going to subtract x from each side. So we've got y minus x equals 3. Now some of you are purists, you're math purists, I love that about you, and you're like, wait, the x isn't before the y. Well, we can adjust that. You do need to change your subtraction to addition. So let's rewrite it this way, y plus negative x equals 3. And then because of the commutative property, you can switch any numbers that are being added together. So this actually is negative x plus y equals 3. And I hope you see the ax plus by equals c format. A is negative 1. That negative sign in front of the x is actually the number negative 1. B is understood 1. That's the number that's in front of the y. And then c is 3. So this is definitely linear. Now we want to graph this thing. So we're going to come over here And I'm going to use the original equation because they already have y solved for. That's what we want. It makes things easier. And we're going to plug in some numbers. So let's do our old standby, -2, -1, 0, 1, 2. You're going to take each of those x's and you're going to plug it into this equation. So let's take the -2 and let's plug it in. What's -2 plus 3? If you said 1, you are correct. What's -1 plus 3? 2, 0 plus 3, 3, 1 plus 3, 4, and 2 plus 3, 5. So there you go. That's what we're going to graph. So let's get our graph paper, or if this graph paper showed up on your notes, let's use this instead. And let's start graphing these things. All right, so let's do -2, +1, -1, +2, 0, 3, 1, 4, and 2, 5. Excellent. That looks wonderful. And then, of course, just draw a line straight through it. And there's your graph. It looks wonderful. You did a great job. All right, let's look at letter B. Y equals x squared. I'm going to write it real big so we can see it. And we have a big problem. Do you remember on the last page when I told you that x and y have exponents that are an understood 1? If they do, then it's linear. If they don't, like in this case, x has a square on it, guess what? This is not linear, and we're not going to graph it. Okay, sorry about that. That popped up. I don't know where that came from. So let me see if I can get this down and out of our way. All right, here we go. We're back at it. Sorry about that. I must have hit too low on the screen. So it's not linear. If it's not linear, don't graph it. Okay? All right, let's get to our last example. This is an application problem. Sue, I'm going to read it to you first. Sue rents a manicure station in a salon and pays the salon owner $5.50 for each manicure she gives. The amount Sue pays each day is given by the function f of x is equal to $5.50 times x, where x is the number of manicures. We're going to graph this function and give its domain and range. All right, so we already know. We didn't have to figure this function out. They gave it to us, which is a hallelujah. One last thing we got to think about. So we do want to plug in some numbers, and let me ask you a couple questions, some leading questions. First of all, can you do negative numbers of manicures? Boy, I hope you said no. So we can't do negative manicures, but we can do none, and we can do whole numbers, and that's what we're going to do. The least number of manicures that she can do is 0. She doesn't have to do any. And so she wouldn't make any money, and she wouldn't have any rent money to give if she didn't do any manicures. If she did 1 manicure, she would be paying $5.50, 2 manicures, $11, 3 manicures, $16.50, and 4 manicures, $22. So I hope I've impressed upon you that we need these numbers to be whole numbers, first of all. They can't be negative because you can't do negative numbers of manicures. Now, let's prepare a quadrant 1 graph, okay? Let's prepare a quadrant 1 graph. Now, a quadrant 1 is just upper right. Both values are positive, and our x-axis is going to be number of manicures. Number of manicures. And we're going to go by ones because these are whole numbers, and that's all she can do. Whoops, what happened? I guess I was a little too low on the screen again. So if this keeps doing it, then I'm just going to go to plan B, which is right above the line. Sometimes if I get too low on a graph, it gets a little squirrely on me. Okay, now your y-axis is going to be your rent. You know, Sue's rent, how much money she's paying for each manicure she does. I really don't care what your increments are. My advice is, please, for the love of God, don't go by ones, or you're going to have a really tall graph. So let's go maybe by 5s, or if you're really ambitious, you can go by 550. That's fine. I don't really care. I'm going to go by 5s, and if you want to emulate me, go right ahead. And here we go. Let's start graphing in some of our points. We've got 0, 0, 1, 550, so just go slightly above the 5. 2, 11, go slightly above the 10. 3 is 1650, so estimate it where you think 1650 would lie on that particular line. And then 4 and 22. Now, your book, if you're looking at your textbook at all, your textbook graphed a line through those points. And remember what I told you, hey, this is discrete data. We don't draw a line connecting these points because you can't have or do half a manicure. Your book did the line because they wanted to show the trend continues into infinity, is what I read in your book. I'm a purist. I'm going to stay with, hey, this is discrete data, and we're not going to connect the points, okay? So we graph the function. Now we're ready to identify the domain and the range. Now the domain, don't let it freak you out. It's very simple. Go back to your chart. We started with 0, and we wrote 0, 1, 2, 3, 4, and then to continue this, just do and so on, dot, 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 and so on. That indicates that this type of information continues into infinity. And then your range, do the same thing, go back to your chart. We're going to go 0, 550, 11, 1650, 22, and so on in that pattern. And that's how you do domain and range. We're not going to do inequalities because inequalities indicate numbers in between the numbers, and we don't want to indicate those numbers in between. You can't do half a manicure. So we're not going to use the inequalities. We're going to use these numbers in those patterns for the domain and the range. Okay, this is the end of our lesson. The rest of the pages are all pages that you can do on your own. This first page is from example 1, and the second one's example 2, third one's example 3, fourth one is example 4. So try those on your own. If you get stuck, don't worry, don't stress. Just come to class with your questions. Write down where you're confused so we can talk about this together. Have a great night. Thanks for listening.